and biovoxel. And just a reminder, you can use those filters in 3D with the 3D plugin. Okay, so in the plugins 3D menu here, you have your fast filters right there. The filter check in the biovoxel allows you to change your kernel size from, say, an array of different sizes, and then look at how it affects your image. All right, question period before we move forward. Any questions, guys?
Don't think there's anything.
No questions so far.
Okay. So moving on, I want to introduce a bit of a more advanced tool here. That's also the pre-processing filter type, and it's called the fast Fourier transforms. So essentially, you can look at an image in real space, okay, or space domain, and you can transform that image with mathematics called fast Fourier transform to look at your image in the frequency space or frequency domain. So essentially, let's say you have a few large stripes oriented vertically. How is this going to be represented in the frequency space is going to be represented by a few dots aligned along the horizontal and close to the center, because they're fairly large stripes. If you have more stripes and oriented the other way, then you've got an orientation dependence on the frequency space. And also you can see that the high amplitude points are further away from the center. So essentially, I'm not going to go through the details, but the fast Fourier transform picks up patterns in your image. So you can think of your image as being composed of a bunch of patterns of lines or whatever you want. And so it's able to pick up those patterns fairly well. And you can see it's orientation dependent, okay, and frequency dependent in the way that this is high frequency, so many stripes, and this has less stripes, so low frequency. So essentially, you can use those this frequency space image that you can generate to modify your image. So if you mask everything, so you don't care about the high frequency information, but only about the low frequency, you can end up with a smoothed image. Versus if you eliminate the low frequency and just gather the high frequency, you're going to highlight your details. Okay? And one really useful tool with the fast Fourier transform, because it picks up pattern, it's really useful in slide scanning, where you have many images that are tiled, and you can easily see the shading effect between each image because of the roll-off. So one way to correct for this and show it in your paper is to use the fast Fourier transform. So we're going to open the mouse kidney and the mouse kidney fast Fourier transform mask. Okay, so that's just our initial image, and we're going to try to attenuate the shading bands right here. So essentially, open the mouse kidney and the mouse fast Fourier transform mask. And we're going to go into the process menu, FFT for fast Fourier transform, and then generate the FFT of the mouse kidney. Okay, so that's our frequency space image. And so if I look at the graph or the line of the intensity here, I can see that there's dips. Okay. First, close to the center, and then a few high points and a few dips. So basically, these are representative of our dark stripes, okay, the high points here. So I'm going to try to eliminate those just at the low frequency, because they are fairly spaced out, so that we kind of flatten that image. So what we're going to do is we're going to do a multiplication, and that's going to be done by the image calculator. So process image calculator. Sorry, I'm just going to move my stuff so that you guys can see. Image calculator. Okay, so we're going to take our fast Fourier transform, multiply it by our mask, okay? Don't create a new window, just hit OK. And there's our mask. So we're masking the low frequency along these, the vertical and the horizontal, because our stripes are in the horizontal and vertical direction, respectively. And then what we can do is just inverse Fourier transform. Zoom. All right. So we attenuated those stripes. Of course, we could work it out a little bit better, but that's one example. All right, we can also work on other, so I talked to you about masking low frequency or high frequency. So you could do a fast Fourier transform of this image and then mask the low frequency, okay, so that you highlight the details or the edges, okay. You could also mask the high frequency. So if you highlight, if you put a mask in white, basically, in Fiji, basically it takes care only of the the region that is masked with the white. And so this leads to some smoothing. Okay, so that's called the low pass filter. And of course, you can use a band pass filter. So in the process FFT, you can do both at the same time with the band pass filter right here. Okay, so you can take care of some of the stripes here with the low frequency, and you can smooth some of and by getting rid of the high frequencies. So now I've added fast Fourier transform masking for the background, for smoothing filters and sharpening filters. Okay. Moving on to binary or post-processing to refine our segmentation. Okay. Here I highlight the post-processing, but because we're gonna tackle morphological filters, and these traditionally have been defined for binary processing. However, we've got now tools, morphological tools that allows for pre-processing as well. So you can use the morphological filters on grayscale images. So here's an example from last week where we used the watershed object separation to separate our objects. Okay, so this is a morphological filter that looks at your different objects, and the watershed is really good for ellipsoid type of objects, not so good for non-ellipsoids. So biovoxel is a watershed irregular feature right here to take care of this. Okay. So what are morphological filters? So the watershed essentially looks at the distance map of your object. So first of all, it assigns a grayscale value for each pixel, depending on how far this pixel is from the background. Okay, so background being here, this pixels are low grayscale value because it's close, and then higher up. Then it will erode these different blobs so that to get to the ultimate point. And so for this, for example, we're going to get 2 ultimate points. For this one, only 1. And based on this, it's going to regrow it. So it's going to dilate these ultimate points to generate two objects for those that have 2 ultimate points, and 1 object for those who have not. So in this way, I talked about eroding and dilation. So those are 2 basic morphological filters. So how do these works is if you have an object here and a probe or a structure element, which is a kernel essentially of a certain shape, you can use that probe to either add some pixels to your object or erode some away. Okay, so essentially it looks at the probe in the decursive dilation and looks at if the probe intersects with the object. If it does, it's going to add some pixel. If it doesn't, it will not. And here it's going to be whether that probe is contained within your object. If it's contained, it's going to erode, and if it's not, it's going to leave it as is. So I say it can be applied to grayscale and binary. Traditionally, it was binary only. So let's look at how this affects our dot noisy image, just to have an idea of or feeling of how this works. All right, so we've got, I'm just gonna pull this out. Oh man, I forgot to record, I think. Oh no, I'm recording, that's perfect. So that's gonna be available later. Okay, so let's delete the center of this object, okay, just to show you the principle of the morphological filter. And what we're gonna do is we're gonna threshold this and go down to 9 just to generate a binary image. Okay, so we're going to work on the binary for this part. And so now I want you to go to process binary erod. Okay, so that's binary erod. You can see what happens. So basically it removed my noise, but it also eroded my object and eroded the center because there was a hole in the center. Now, if I do the opposite, okay, which is the binary dilate, okay, you can see that my hole is filled, but then I merge with my other object, okay? So what happens in morphological filters is that lots of them can change the object size and the topology of them, okay? So you have to be careful. One way, so the next iteration of morphological filters are called opening and closing. So essentially, the opening and closing are succession of erode and dilate, or dilate and erode respectively, okay? So if you start with an image that has some noise that are fairly dark, okay, and you do an opening, which is an erode and a dilate, the erosion will get rid of those small dark object, okay, and it's going to smoothen out during dilation, okay? The closing of this object will actually also remove the small dark, but it's also gonna increase the size of that object slightly. And whoops, versus if you have bright objects surrounding your object of interest, okay, the opening will remove those objects, but the closing will not. Okay, so if you're interested in those bright small objects, then the closing might be of interest. You can see also that the size is better preserved than our original example with the simple erode or simple dilate. So I've said at the beginning that we can change kernel size with any kernel type of filter. In the case of morphological filter, you can change their size and their shape, okay? And also the connectivity of the pixel. So in the binary options, so process binary options, you've got, you can actually pass multiple times a certain filter, okay? So that's iteration, and you can actually define how many neighbors each pixel should have to either subtract it or add it. Okay? So that would be a pixel connectivity type of criteria. In MorphoLibJ, you've got, which specialize in morphological filter. Okay, you've got your morphological filters here. Oops, I have no image, of course. Zing. Most of them are designed to do it on the grayscale. And so here you have the shape of that structuring element, as well as how large it is. Okay? So that would be the kernel shape and size. All right, there's other ones, there's other options out there. So process binary, you've got the distance map, which we talked about. It's used for the watershed, the ultimate point as well. And there is the Voronoi in that same menu. So essentially, this is a representation. The black dots are the ultimate points of the blobs. The Voronoi is actually, it draws lines between the points that are, for pixel that are equal distance from neighboring ultimate points. Okay, so that can be used later on in what we call region growing. So we'll come back to it if we have time. So in the MorphoLibJ menu, there's many more filters you can use. The top hats, for example, which are going to preserve small dark objects versus the white top hat. Sorry, the black top hat for dark object, the white top hat for bright objects. And we're going to go through the morphological reconstruction a little bit later. And this is especially good for a region growing type of segmentation, as well as keeping the size of your objects as they were initially. So here's a summary of the morphological filters that you can use. And the tools at the bottom here, the process filters option and the MorphoLibJ plugins. Any questions so far?
I can't see any questions yet.
Awesome. Feature detection and so masking and filtering some features based on attributes. So after you segmented, you refine your segmentation, you can start measuring stuff or measuring different attributes of your object and filter them based on these attributes. So we've seen last week, if you open the blob image, blobs here, thing. So what we're going to do is threshold this image, and then we can analyze those particles. Okay, so I'm going to use what we used last week, 175 in terms of size, and then circularity 0.8. Okay, so this basically, it looks at all these particles, measure their size. Anything that's below 175 is going to be rejected. Anything that's not too round is going to be rejected. I'm also going to use the exclude on edge so that we don't bother with those particles here. Okay. So that ends up with while I have a mask, I had the mask option on. Maybe we show nothing, and then you've got your display here. Okay, so you've got your summary of all your objects and all their measurements right here. I purposefully added some more measurements here. Okay, so you have a ferret angle, you've got some minor and major ellipse size, and so on and so forth. So this is to tell you that you can basically filter those objects based on more than just size and circularity. And one of those menus is the extended particle analyzer in the BioVoxel plugin. Okay. So what we're going to do is we're going to generate the BioVoxel plugin. Unfortunately, works only on the binary image, so you have to use a binary image as input, and then you could do extended particle analyzer and look at this, how many different attributes you can filter based on these object shape and so on and so forth. Okay, so if I hit OK in this case, okay, so I've got my objects right here. Okay, and I've got my measurements. Here I showed that this is a geometrical measures, and you can see here that the mean of those objects, so which is the mean gray intensity level, since it's measured straight on a binary image, it's not representative of actually the grayscale mean. Okay, so for this you will need to do some other tricks, which I'm going to show you. So that's called masking. Just before I show you that, I want to just highlight, if you're wondering which of these to use, you can have an idea with the shape descriptor maps. Okay, so essentially, if I go the wrong way here, essentially you can pull out the shape descriptor map of this guy. So shape descriptor map here. We can watershed or not, so on and so forth. I'm gonna just do this. excluded particles. Essentially, the maps is a stack of, say, area, and it's color-coded by their size, and so on and so forth, and ferrite angle and so on. So you can have an idea of which particle you want to include and which particle you want to keep. And then input that in the menu of the biovoxel extended particle. All right. Now, I've said that we want access to intensity measures, not just geometrical measures. So there's a few ways to do that. And so the first way is a ROI manager. So essentially, if we go back to the extended particle analyzer, you've got the option to add to manager, and that's what I did earlier on. So if I add to manager, essentially, I'm not going to run it again. Essentially, I can look at my different particles here based on my manager. My different particles are highlighted. Okay. So if I go back to my original image, I'm just going to keep pressing 9. It's actually okay, and then I can highlight all of those, show them all. Okay, so and with the ROI manager here, I show them all here, and then if I hit measure, I'm gonna have my gray intensity level, mean gray intensity level measured as well, because now we're measuring on the gray scale. And if I would like to have kind of stats on this, I can just hit result summarize. Okay. So that's one way of doing it. The other way would be to redirect. Okay, I'm gonna just go like this. So the redirect, and I'm gonna get rid of that as well. The redirect essentially redirects your measurement to another image. Okay, so redirect to initial blobs instead of blob 1, which is my mask. So initial blobs, and hit OK, and then there you go. All right, so that's how you would mask your original image. And you can use that. You could use that if you have 2 different channels. For example, you just have all your region of interest, but you measure it on another channel, for example. Does that make sense? I guess I won't get the answer. Okay, so that's just the summary slide. So redirect. And you can do that in 2D or 3D. So I'm going to show you how to do this in 3D with the ROI manager. Essentially, I'm including this here because it didn't work last week. So I'm trying to show you that ImageJ can actually work in 3D as well. So here we go. So we're going to include some stuff that we've seen last week and so on. And I want to highlight the use of the 3D manager, okay, in the 3D ImageJ suite, okay, which is this guy. So essentially what we're going to do now is we're going to open organ of Corti and then process it so that we get, we highlight or we segment the nuclei. So if we go organ of Corti here, okay, open it up. First of all, we're going to split those channels, and we're just going to work with 2 channels. Okay, split channels. Let's get rid of the gray one and the blue one, and work only with the blue, the red and green. So now what we're going to do is, just because there's compatibility at the end of this, I'm going to change my image type to an 8-bit, because this is a 16-bit. Sorry. All right, so what we're going to start with is we're going to do a mask based on the nuclei channel and then apply it to the original image. Okay. So let's start this, and we're going to start by smoothing our nuclei so that we get nicely defined objects, and I'm going to do that in a 3D way. So I'm going to use a 3D plugin called 3D Fast Filters, and we're going to do it a 2 by 2 by 2, okay, mean. So that will generate a filter that is an image that is smoothened in 3D. Okay. And then what I'm going to do is I'm going to use the thresholding, just a regular 2D thresholding automated to generate my mask. And the idea here that why do I use the 2D? I could use the 3D ones. The 3D tools have fixed manual filter thresholds. So essentially, you fixate the lower value, and then this applies to all your image, instead of an automated one, which figures out based on your image contrast or your image SNR. So that's why I'm going to use the 2D, okay, and I'm going to apply it, calculate a threshold for each image in case in my Z stack there's some image that are a little bit lower SNR, and there you go. You've got a binary image now of your nuclei. Then what we're going to do is we're going to eliminate some of the mess here and the borders, and for this we're going to simply use our tool here. Okay, we're gonna eliminate based on size and circularity. Okay, and exclude on edge. Okay, and then we're going to generate a mask so that we get a nice mask of this image. So there you go. You've got your nuclei. Okay, it's not perfect, but let's say for this demo, it'll be all right. Then in order to use the 3D manager that I talked about in that next step right here, I'm gonna have to generate what's called a count mask. And the way I can generate it here is through the plugins, the analyze 3D object counter. Okay, I'm gonna generate object surfaces and this automatically generates a count mask instead of simply a binary. So the count mask essentially is color-coded based on your particle number. Okay, and that's what is needed in the next step. So that's why we're doing this here. And like I said earlier, you could have thresholded here instead of applying your automated threshold, but this is a manual threshold, as you can see. So if I hit this, then I've got my object map. Okay, and if I can adjust the contrast, I've got my object. Or my surface map, where I got my surfaces. Okay. All right. And so now I'm going to move on to the 3D manager, which is through the 3D plugin here, 3D manager. And there's the window of interest. So I'm going to use my surface, doesn't matter, or my object. To add that image to do my segmentation. The 3D segmentation here is a simple threshold. Okay. So now I've got my 3D segmentation, and if I select all and hit measure, this is for all the geometrical measures, okay, of all my objects. If I hit quantify, this is my intensity base, and you can see that there's something wrong with the mean again, okay, because we're applying it to our mask, not our original image. So in that case, we will need to go back to our original image and apply that mask in basically the same way as with the 2D. So if I show live ROI, okay, I've got my ROI here. I can select them all, and there they are. Okay, so now if I hit quantify 3D, I've got my mean intensity of all my objects here. Awesome. All right, so now if I want to make fancy pictures or make fancy videos, or quasi-fancy, it's nowhere close to immersive, but I can merge back some of the channels. So I'm going to use the channel tool. That's the last step here, merge channels. Red and green are already selected. I can add the gray channel, and that could be, say, my objects here. Okay, I'm going to keep the source image in case this fails. And there you go. So you've got your different objects that are highlighted. Okay, and like we talked last week in the Stack 3D project, you can do a quick animation of that. Yeah. Okay. Of course, you can adjust your brightness contrast here, okay, for each channel. Okay, then you could save that. So that's the 3D tools for you. Okay, moving on. How much time do I have? 10 minutes. All right, I want to go through quickly the object with an object type measure. And I'm gonna, leave out the region growing and just show you the slides. So this is basically one use of masking again. So essentially, we can look at the punctates within each nuclei to basically calculate DNA damage. So in this image, we can smooth it out right away just to eliminate some of the noise. Okay, and then split it into channels. Okay, with our channel tool. The blue, let's forget the blue and just work on these, the red and the green. And then I'm going to duplicate each, just because now I want to generate a mask of each of them. Okay, that we're going to reapply on the original later. Okay, so for the red channel, we can threshold this. Okay, and apply. Okay, and then you can see that there's holes here, so I'm going to show you another binary processing that we can do, fill hole to get rid of those holes here. On the green channel, we can use the on-chart mask, okay, in the filter to highlight those punctates. Okay, there they are highlighted. Okay, then we can threshold this thing and maybe apply a quick watershed. It's not going to be perfect. This image is slightly lower. As you can see, those are fairly big. And then you could do everything manually and measure with the ROI manager. The BioVoxel has this speckled inspector, which is pretty neat. So essentially, you've got your big object, which would be your red one, and then your small object, your green one. Okay, and then we want to redirect this to the green image to say measure the intensity of our punctates. And then you've got some object filtering here. Okay, so just as an example, I'm going to input some circularity criteria, a number of speckles that needs to be detected to be valid, and a maximum number of speckles per nuclei, as well as a minimum speckle size. Okay, you can use your ROI manager as well, and then hit OK. And so there you got all your stats, and here you get a little representation. So in the first nuclei, there's 19 punctates. This one has 18. This one is not passing our criteria of 2 here, so it's out. These ones neither, because they are over 20. That's one way to do some kind of object into objects measurements. All right, region growing. I wanted to go through it, but we're just going to talk about it slightly. So essentially, region growing means I'm going to generate, usually it's multi-channel type of segmentation where you generate seed points, in this case, the ultimate points, for example, in one channel, and then you use those seed points to grow region in the second channel. So for example, you could use your nuclei here as seed points to grow and define your cytoplasm marker. So MorphoLibJ in MorphoLibJ tools, there's the morphological reconstruction. That's really one really nice tool to do that. Essentially, you've got a mask object, which is your object of interest, which is going to define the limits of your region growing, and then you got your seed points. And the seed points grow until they reach a criteria of the limits of this. Okay. So here I applied it. If there's no seed, so I deleted some of the nuclei here and here, then these are filtered out. Okay, and vice versa. The binary, or not vice versa, but another tool would be the BioVoxel binary feature extractor, which works on binary images. So again, if you don't have any nuclei here, which are your seed points, then these cells disappear. All right, so that concludes for the object filtering and masking. And here I have a summary of the tools that we've looked at. Those are going to be available so you can review them later on. So you can see that when you look at the classic image analysis workflow, essentially the steps 2, 3, 4 can actually be cycled through with masking, right? So you segment initially based, say, a binary image, you process that binary image, and then you mask, you use that binary image mask to resegment your objects, and then finally measure. All right, we have 6 minutes for a quick overview of CellSense, and then I'll pass the mic to Calvin. Any questions at this point? I'm gonna start moving my screen. Hopefully this works.
There are no questions so far in the chat box.
Awesome. All right. Where's the CellSense? There it is. All right, so quick overview of CellSense, and I won't go through all the tools, but essentially, this is your CellSense window. And so the tools that you want to have, I'm just trying to make this slightly bigger here and there. I got it now. Tools that you essentially want to have are how to adjust your image for viewing. This is just viewing purposes. So for example, I could crank up the contrast, okay, here, okay, or just leave it in the low contrast. Your image property, which are going to define how many pixels, how this image works acquired, and if there's any calibration. And then you're interested mainly in that count and measure here. You also, I mentioned some toolbars here, if you guys see it, that might be of interest to you. So essentially, when you start processing an image, either in Fiji or another software, you can duplicate that image so that you keep that original image intact. Okay, so I duplicated this through the image menu, duplicate, or Control-2 right here. And you can see that in the image menu, you've got your adjust display again, different modes. You can resize the geometry, you can crop that image, you can calibrate that image. And you can combine and separate channels. So we'll hit channel, separate the channels, and basically it's going to generate 2 channels, my green and my blue. Okay, I'm just going to work with the blue today. The next step would be some kind of pre-processing. Okay, so the process menu is all about this, pre and post processing. Most of these tools will work on grayscale image. Okay, so what I'm going to first do is apply a morphological filter to separate some of these objects. Okay, and so what it does is it opens a window where I can see my different objects. Okay, I like to have the burn white on to see how these are going to separate. Okay, so here that's not good, but here that's pretty good. Okay, so the filter, the kernel size is basically your fine coarse menu, and the smoothness means how these lines are going to separate the different objects, how smooth they're going to be. Okay, I'm going to just leave it like that, and then create a new document of those separated objects. So there's my new image, which hopefully is separated as I seen on the previous screen. So at this point, I'm ready for segmentation. I just have to double check what kind of measurements I want and how this segmentation is going to be done. So if I hit the options, this little icon here, I can look at my detection, okay? So whether this is pixel connectivity, so whether it includes diagonals, so 8 pixels, only 4. Am I going to do my detection on an ROI or on the full frame? Okay, so if I have defined an ROI with these tools up here, that would be an ROI detection. Am I going to include or exclude the borders? And I can filter by object size right away, okay, if I want to. I can define my different measurements here, okay? There's a bunch of measurements available. I just need to click on one and then add it. You also have class measurements, which is relate to classes of objects. Essentially, if you have different channels, for example, or if you define classes based on size, for example. So you could access their measurement. And ROI measurements, basically statistics on the ROI. So that would be an example of a class defined by area. I'm going to actually use phase, which is the default. All right. After that, I'm ready to threshold my image and segment it. So you have the automated threshold, the manual one, where you just define your different threshold manually, and the adaptive if you have some kind of issues with the background. The HSB, it would be for saturation for bright field image type. So if I hit the automatic threshold, I can see here how my image is going to be thresholded automatically, okay? And so, and I can have multi-band pass by adding another phase. So the first phase would be from 60 to 136 gray intensity levels, and then the second one, which I could call something else, would be anything higher than that. Okay, I'm not going to use 2 in this case. And then I can hit count and measure, and and basically it generates a detected object and then populates my object measurements at the bottom here. It also gives me a total count of objects, and I can edit those objects. For example, I can select some of them and look at their measurements, okay? And I can delete them manually if that's if it's impossible in any other way, or I can segment them, split them. I can also look at the object filter, which is filtering by the different measurements I define. For example, if the area is something that I want to look at, I can refine my objects based on area. Okay. So this is the histogram of all my objects. I can say, okay, I want anything bigger than 400 and so on and so forth. The class measurements would appear if I have more than one class, okay? And then you would have a histogram of the different class in the class histogram. If you perform the measures on an ROI, so count measure on ROI, then they would populate the ROI here. And then you can, at the end, export all to Excel and so on and so forth. Okay, I'm not going to go through the class just because I want to give some time for the decon. So I'm going to stop sharing. Kelvin, the mic is yours.
Thanks, Vincent. I don't think we've lost too many people to research in progress. So let's see. You'll have to tell me if this is working. If I share my screen.
Nothing so far.
Okay, give me a second.
Do I have to allow you? Or? Okay,
No.
good. Awesome. Good? Yeah.
Right.
Yeah.
Okay. I'll try and get through this as quickly as I can. So basically, there was a nice intro to, was it more than an intro to different image processing techniques. And what I'm going to talk to you about today is basically an iteration of that, or perhaps the next step of image processing, which is deconvolution, and how that would help some people, not all. It takes a little bit of work to get to that point, but hopefully you'll find that it could be useful for what you need. So, right, talk outline. I'm going to go through a quick reiteration of resolution and area disks for people who didn't see my first talk, because it's pretty important that you understand the concept before you go on and try and play with deconvolution. Obviously, I'll be talking about the concept of the point spread function, as it is central to the concept of deconvolution. The different noise and image degradation contributions to your image and how that affects everything. The different types of image processing in comparison. Maybe I'll mention, now you've seen quite a few that Vincent has mentioned, and then where deconvolution fits in. And as mentioned, I'm just going to be talking mainly about the image, the software suite that we have, HBIAMP, mainly because we're promoting it because it's very easy to use. There are other programs out there, free or otherwise, but it's what we have, and it seems to be doing a very good job. So there we go. So what is deconvolution? Definition, if we simplify it, is it's a very computationally intensive image processing technique which is used to enhance the signals from the data that you have recorded. If you want to put it in like a mathematical way, I guess, it's that your observed data, what you've observed, can be modeled after a pure signal, which is then distorted by a filter or an external source. And in which case, then deconvolution can be used to reverse engineer that and then restore the original signal from that convolution. And it's been used for quite a while now, namely in astronomy. Microscopy seems to be trailing behind astronomy quite a bit, but kind of just stealing ideas from astronomy step by step, but glad there is somewhere to steal from, to be honest. Yeah, deconvolution has been used for quite a few things, even seismology, apparently. So yeah, I'm going to turn my laser pointer on in case I need it. So the quick refresher of those who didn't see my first talk on what resolution and the area disk is. So resolution is simply defined as the distance, which is d, by which two objects can be separated so that you can distinguish them from each other. So basically, if they're too close to one another and you can't see that two objects are two objects, then you'll see them as one. And it all depends on the diffraction limit and your resolution. When you focus, if we have a point source of light, you never see a single point. You never see that because of various issues, but diffraction is one of them. You see a pattern, is what we call the area disk, which is kind of this central main intense point that is surrounded by these concentric rings, and of which that central point holds most of the intensity, 84%. Then you have the different orders of ringing towards the side, and simply put, that is the point spread function, and area disk is the spread from the point. So as I mentioned, it's all to do with how you can resolve two things if you have two area disks. So this is still resolvable, but once you bring them a little closer together, depending on your wavelength, because the Rayleigh criterion and resolution is defined by this formula here, which is a constant 0.61 times the wavelength divided into numerical aperture. And you can measure the area disk basically by looking at the central peak and looking at the 4/8 half maximum. So that's kind of just what the area disk is and how it's going to be relating to a point spread function. So to put this into a kind of a diagram, a schematic diagram, if you have a diffraction limited scope, which is anything that isn't super resolution, just a regular microscope, you in the visible range at least, you have a diffraction limit of about 200 nanometers, kind of a resolution limit. So you want to look at something that is below that. So let's just use a 100 nanometer bead, fluorescent bead as an example. And as I mentioned, you'll never see this if you look down a microscope. You don't see a clean, crisp 100 nanometer image because that's beyond the diffraction limit. What you see instead is a bit of a blur that represents that. But again, you don't really see that because you have these, because of diffraction and other factors, you see these concentric rings that make up the airy disk. And basically, if you assume that that is the focal point and you kind of focus away from it and then focus towards it past the focal plane, you kind of get these rings. This is all simulated, so it never looks like that. But if let's say we look at this video here, again, you start with a bead function, and then you take a Z stack or an axial stack through that. So if this is X and Y, this is X and Z, and you see this nice, beautiful, well, point spread function, really. And again, you see the central airy disk peak there, surrounded by what would be the different orders of the concentric disks and rings around it. Now, this is, again, simulated. Nothing is ever as pretty as this. So what it really looks like is pretty ugly, to be honest. In the X and Y, again, you look at something like a bit of a blur. In the X and Z direction, you have a elongated kind of a beam there. If you put a 3D projection or construction of a PSF, you get something like this. It kind of looks like a dumbbell, but you can kind of see where what we're working with here is central peak with the concentric rings. And this is essentially a PSF. When people talk about PSFs or point spread functions, you're talking about this. So yeah, so that very quickly is a point spread function to really distill it down. Just to bring it back a little bit, if you look at the 4/1/2 maximum of this point here, it roughly translates to your Rayleigh criterion or resolution limit, which is a 0.61 lambda over NA. So this is just bringing you back to that original equation there. So what exactly is deconvolution? Well, let's talk about convolution first. So if you think about what you see as an observed image, which if you see that as an observed image of G, it really is a convolution between your point spread function overlaid over your real object. So what you actually see is a convolution between these two. And of course, you can bring it back into the Fourier space. Not really important right now, but that's how things are done to kind of speed things along to do the deconvolution. But this is not really, this is oversimplified because there are lots of image degradation sources that you have to deal with on top of all of the PSF kind of shapes and everything like that. So I've kind of taken this off a site. Basically, they say there's 4 different types. Most important, I think, is the noise. But well, we're starting with the noise. If you can really say that there's 3 types of noise, the first would be from your digital or electronic device. So basically your digitizer or your the analog to digital converter that comes from your camera or your PMT or your detector, which we call a shot noise. There's signal dependent noise, which is a Poisson distribution, and then imaging system noise, which has a Gaussian distribution. Scatter is another type of image degradation, which is pretty much caused by refractive index changes. So it all depends on your specimen, how thick it is, what it's mounted in, what it's embedded in. So that's mainly specimen and refractive index. Glare is less of a problem now because of the advancements made in coatings and anti-reflection coatings, but usually glare comes from all of the optical elements, such as the lenses and filters and prisms. And blur is basically diffraction. It's the spreading of light through your optical path of your imaging system. So convolution really is what we saw before. It's the PSF time and your object. Then you add in the another convoluting factor of noise, and that's what your observed image is. So the job of deconvolution is basically to work out what your PSF is, noise which is labeled as quasi-random, that if it has a distribution like a Poisson or the Gaussian, you can figure that out and take that away, or take that into effect. So before I go into deconvolution, I have to hark back onto sampling theory again, because it is very, very important for deconvolution. Basically, if you don't sample properly, you have no chance of doing any deconvolution. And not to say that it is only for deconvolution. In my first talk, I tried to really hammer it in that if you're there for a short amount of time just trying to rush through things, then you're going to end up with garbage, and your measurements and your image analysis is going to reflect that. So, but it is especially important in deconvolution. So to really rush through this, both of these sampling theorems basically say the same thing, which is you need to put down approximately 2 times. You need to sample 2 times of what of the limits of your system. So if you have an object that's 100 nanometers, you really want to be putting down 200 nanometer. No, hang on a second. Take that back. I had that backwards. If you have a 200 nanometer object, you want to have a 100 nanometer pixel and 2 of those over the top of that. Yeah, sometimes it does get confusing, but if I want to bring that into more of a diagrammatic representation, if you have an analog signal and you try and sample that a little bit rough, then yes, you do have some idea of what you're dealing with here, but it's not really representing that analog signal. So you really want to be sampling as best you can to represent that original signal. If you want to see it in terms of an image in the spatial sense, you want to be putting down enough pixels to represent your image, as this will imply. And you never want to forget about Z. In fact, Z is very much, it's very important, because if you're dealing with PSFs, you're dealing in 3-dimensional space. So you want to make sure that you take enough slices to represent your axial volume if you're doing that. So there is a case of oversampling as opposed to undersampling. So it is true that if you oversample, you don't really add any spatial information or resolution, but it really does add more accuracy to feature measurements, and it does increase signal to noise ratio. And when you're dealing with deconvolution, we'll see why this is so important. But even though the Nyquist sampling theorem kind of says that you want to have an interval of 2 times for the smallest resolvable feature, it is actually suggested that you want to have 2.5 to 3 samples for each smallest resolvable feature. And if you go to this link, which is a Nyquist calculator, now a lot of microscopes already have their own little button that helps you kind of automatically set all your parameters to make sure that you're sampling in the Nyquist rate. That all takes into account your optical parameters, your optics that you have, your excitation, wavelength, everything like that. This calculator, because it's by the company or the manufacturer of the deconvolution software, they want to make sure that you have the best chance of getting the best deconvolution. So they go a little bit overboard. So you can just go there and type in, but you do need some data to go into that. So you need to know your microscope type, numerical aperture of your lens, excitation emission wavelength, so on and so forth. If you put that in, it'll tell you how small your pixel size needs to be in the X, Y, and Z for you to have a decent shot at a good deconvolution. So what are the types of image processing? So Vincent's gone through quite a few of them, but I've kind of just thrown them into 3 very general categories. You can call the first one enhancement, which some examples would be denoising and filtering, such as Gaussian and averaging. So this kind of enhancement will reduce the noise or will smoothen the image, but will actually end up blurring the image because of that. There is no resolution increase, and it's actually more likely to decrease the resolution. If you look at the blur removal techniques, such as nearest neighbor, computational clearing, it does reduce the background and blur, but noise will still remain. So technically speaking, you can just combine these two. There is no resolution increase, but it has been shown that blur removal has the potential to remove useful signal, which is not great. Then you have restoration image processing techniques, inverse filter decon, iterative, non-iterative, and then I've bolded this here because that's what we're going to focus on, maximum likelihood estimation decon. And these kind of restoration techniques removes not only blur, background, and noise, but with MLE, you can actually end up increasing your resolution given the right sampling parameters and other factors. Say a quick example here of a raw confocal image. If you throw in a background subtraction and Gaussian filter, you do get rid of a lot of the noise here, but you can quite plainly see that you lose a little bit of resolution, a bit of blurriness turns up, so that's kind of the downside. If you use MLE and deconvolve it, you get the noise and background gone, and it seems as though you get a little bit of a resolution increase here. So now this is provided by the SVI software people. It seems a little bit like an ad. You never believe anything because, of course, you always have to be skeptical. But having used it quite a lot, it does have very good results. But just to be wary that it's not going to be as perfect and beautiful as that. So at least in the Huygens software, or MLE is an iterative deconvolution process where, as the name suggests, it iterates and iterates and iterates and iterates until it gets to a point where it's reached a, well, in this case, they call it a quality number, which can be set by you, or there's a default there, but it's just a threshold that it reaches. So you can start it off and it'll it keeps iterating from certain points to try and find the best kind of result for you. So moving along to the different iterations, you can see that as it iterates, it gets better and better, then it hits a kind of a plateau and you don't really get much in return, so kind of diminishing returns. But as it says here, very quickly, because of the quite obvious noise in the background, you get quite a big jump in the beginning, and then it kind of smoothens out. Just to mention that the default is actually around about 20 to 40 iterations, which is kind of interesting because even the company itself encourage you to use up to 100 iterations, or at least get a quality number of that gets you to 100 iterations. So that's something to keep in mind. You may not need it, but yeah. So the different variants of MLE, at least there are 3 that we have access to in the Huygens software, which is classic, goods, roughness, and quick. As you can see, classic here is the default algorithm because it's very robust and you can just throw just about everything at it and it can handle it. Goods roughness is faster than classic, although it uses more RAM, which is not an issue for us. We have 256 gigs of RAM, so not an issue. But it's good for high noise images. We prefer you didn't come with high noise images, but that's not to say that you had a choice in the matter. You could have some weak signals inherently. Quick, same, it's faster, but I don't know this is a pro or not, but it's only good for low noise images. So not really recommended, as you can see here. So you can see the CMLE is good for just about everything you throw at it and all the different types of microscopy techniques. So what can you use this for? The applications are basically anything with a PSF. Wide field confocal. This figure here just shows you the simulated or generated PSFs, so to speak, of all the different microscopy techniques. So yeah, you can use it for just about anything. Wide field confocal, spinning this, light sheet, and even STED and other super res techniques can benefit from this because even though they're super resolution, they still have their own PSF, which means you can use it. And I've seen very good results from deconvolved STED images as well. The software, as I mentioned, a lot of companies have Nyquist sampling parameters, and nowadays a lot of companies, a lot of microscopy vendors have their own version of deconvolution on there. It's just something that they felt the need to do. Now, they're not all MLE based. They may have their own little thing. But at least in our facility, we have, on our Leica, we have Leica's version, which they call Thunder. And on our Nikon A1, I believe we have a 2D only deconvolution. Offline, we have an offline Nikon license that does that. Again, with CellSense, I think has a 2D decon on there, but I'm not sure. We may have had a demo and got it taken off. But and of course, ImageJ Fiji has plenty of decon modules there and plugins. So you can go to that. This is a good start anyway. You can just go to this link and it'll give you a rundown and what you need to download. Be aware though, as I've mentioned right off the bat, that it's computationally intensive. So if you have an old shitty computer, then it's going to struggle a little bit. And yep, bolded here is the software that we have that we would like to, well, not exactly promote, but we encourage because we bought it for a reason. And the reasons being, well, just to mention that the lifestyle imaging facility also has a copy of this. Our version is on workstation 6 in the facility. We like it because it's GPU accelerated. I won't go into that too much, but all that says is in the past, graphical processing units were mainly for video processing mainly, but it was hard. They had inherently many more cores in the thousands. Well, nowadays they have 1,000, but they always had many more cores in the CPU. And people were wondering how we can leverage all that. And it's only recently that the code has been out there to be able to use all of this, all the cores within the GPU for kind of the heavy lifting. And that's what Huygens has done. The bigger your card, the faster it is. And we have a decent card that will do all the heavy lifting and really speed things up as opposed to doing everything on the CPU. We like it because it's highly streamlined and super easy to use. It's just click, 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 and it's gone and it's done. It has batch processing, which we like, which means that you can literally load up all your images and just press go, which really helps. You don't want to be sitting there because it does churn out the data a little slowly sometimes before it starts to speed up. So it's good to have batch processing. It does accept a wide variety of file types. You can see there's a lot there. What this just means is that you can drag and drop just about everything from any device, any microscope onto this program, and it'll look into it, bring it up, and then you can start your deconvolution straight away. And then you can save it in various formats. Now these can get pretty big, especially the HDF5. So because it also has to convert the file into a 32-bit float. And but nowadays space is cheap, so it's not too bad. You can also downsample it if it's just for a presentation, so it's not such a big deal. So we have a module called the PSF distiller. Before I talk about that, the thing about Huygens is that it has two ways you can go about it. If deconvolution is all about trying to get the convolution of the PSF and reverse engineer that, you want to have the best representation of your PSF. So what do you do with that? Huygens has a way of generating one. Basically, you give it as much information, including the metadata of the image, about how you took that image. And it will come up with the best simulation or theoretical PSF that it can. And you can go forward with that, which is the quickest way, and we get really good results from that. Because there's nothing that compares to actually getting a measured PSF from the system you've used, because there's no lying, there's no simulation. It is what it is. So PSF distiller, what it does, it makes things super easy. Instead of trying to find a tiny bead to try and find a perfect PSF, what happens is you can take a whole bunch of them in a big field of view, and you just give it to the PSF distiller, and it will take and choose all the best ones within that plane and combine them and give you one nice PSF. And from that point on, you can save that and reuse it as many times as you want. That is, of course, something happens to the system and you need to take a new PSF. So that's pretty good that way. again, the batch processor, we like it because you can use both either theoretical or measured, and it's not stringent. You can put in different microscopic templates, as in you can throw in wide field, stuff from confocal. Batch doesn't really matter. And then you can have different deconvolution templates. And for whatever reason, you can start it at a certain time. So very simple, and it will do what you want. You have full control over this, as if you were doing every single image. We do have Batch Express. It's cool that it's an unsupervised real-time decon. Basically, what you can do is, as this thing shows, you can have a watch folder, a network folder that you can save as you're imaging and saving your files to a particular folder. Huygens will keep looking into this folder and automatically deconvolve it and give you a result. So it's kind of on the fly. The bad news is it is kind of a little bit too much hands-off. It uses default parameters and only theoretical PSF, so you don't have much control over the decon process. But if you want something really quick, this is the way to do it, and we can help you set that up. This is the obligatory show-off slide to show the results of deconvolution. There's wide field there, there's confocal there. You can see that quite glaringly straight off the bat that it does get rid of noise very easily, and that's probably what we're most impressed with, is just getting rid of the noise, and the background really kind of pops out your images. But especially in this image here, you start to see that you do get a bit of resolution back as well. So, and I think the one thing that the one group of people that would benefit the most, I think, is the crowd that wants to do co-localization. And I mean, almost every week or so, someone wants to come up and do co-localization with zero idea of how to do it, or at least they're doing it and have no idea that it's a lot more complicated than it actually is. If you want to see if two things are on top of one another and saying that they coincide or they are co-localized, you have to remember that the microscope is not a perfect system. And not only that, the images that you get are convolved, again, with a lot of different noise artifacts and the PSF being imperfect. The full co-localization webinar will be next, but very simply put, one of the measurements you can have for co-localization is the Pearson coefficient, in that, -1 that is not correlated, and then of course +1 that it is. So you can see here that this is the raw data, and this is something that they've used, the inverse filter algorithm, which is one of the image processing techniques, and this has been deconvolved with an MLE from Huygens. You can see that the Pearson coefficient changes so much between them. So just to be wary what you're dealing with. If you have raw images, you have one thing there. This is not even thinking about the last thing which I'll show you about, which is chromatic aberration. In the 3D space, again, in the raw, for these beads, the Pearson that you got was 0.1, but if you deconvolved it, the Pearson changes. So that's something to think about. Kind of the last slide before the summary is chromatic aberration. I did talk about this in the first webinar, but it's basically that not the microscopes that you have, again, they're not perfect systems, and glass doesn't always focus all colors into the same space. Glass is very good at what it does, but when it comes to colors, especially on two ends of the scale of the visible spectrum, it's very hard to focus it into the same spot. And if that's the case and you're running away doing co-localization and just assuming two things are on top of one another, then you're going to have a bit of trouble, because here we have a tetraspec bead, which is, as I mentioned before, we use that for generating PSFs, but it's also great for checking for chromatic aberration, because these beads are basically 4 colors in one. And with the 4 colors in one, you really should be getting a single point like this, but most of the time you get something like this, which is bad. So we have a module on the Huygens Essential that can correct for this, and what you do is simply you image it, take a very good image of these beads, then you correct for it, or at least the module, you just press go, and then it kind of overlays everything back to where it should be. Save that template, then you simply apply that to every subsequent real image that you've taken. In that case, then you have a little bit of a better idea of whether or not you have issues with chromatic aberration. Gradations. MLE is the most robust type of iterative deconvolution technique. There are obviously lots out there. That was weird. It says my internet is, oh well, it's gone now. And I'm almost done. It does require sampling on the Nyquist scale, at least more than Nyquist, at least Nyquist. And if you go to that calculator that I had as a link, then you can see that it's pretty serious business. That being said, quite obviously, you have to increase your acquisition time, and there is a likelihood of photo bleaching because you're sampling so densely. Because of that, we don't recommend it for live imaging, although things are getting better with better detectors and whatnot, but at the moment, probably not. It is highly recommended for co-localization. As you can see, it does affect the Pearson coefficient and other coefficients, I imagine. And the file sizes tend to be quite a bit bigger. But yeah, it's not something that we can't handle nowadays. So that's it. The next one will be on the 8th, unless otherwise mentioned, on co-localization. And we will try and put the slides up and any recordings, if we haven't messed it up, in the news and events archives. So,
quick question, Kelvin.
Yeah.
So when we import the PSF, when we need the PSF, what kind of options do we have? Do we need to measure on the microscope, or can we theoretically generate PSFs?
So you can, the theoretical PSF is a default. If they assume that people don't have the time because it's a little bit on the difficult side to measure the PSFs with the tetraspec beads. So yeah, at least with the use Huygens, if you use Huygens, then it does have a way of generating a theoretical PSF based on your metadata and all the information that you could give it. I know that ImageJ also has a way to make theoretical PSFs. I tried it, and it's it's a bit slow depending on what you're making. So yeah, you can do both.
Yeah. So so what we've experienced with Huygens especially is that when you actually measure your PSF, because the PSF is exactly how your particular system behaves, then we get better results. So we can help you measure PSFs, and we have some PSFs available for different systems so that you can get experimental type of PSF for your decon.
I'm going to leave that slide up.
Cool. So is there any more questions before we close this?
Sorry, that ran a little bit over time. I guess we have a lot to say. So I don't think we lost too many people to the research in progress.
Yeah, that's pretty good. Okay, so stay safe. Thanks for listening to us. Hopefully you learned something, and you can apply it in the facility or any facility you're at. Like Kelvin said, next one is co-localization, so that should be interesting. And yeah, stay safe and all the best.